NASA's Parker Solar Probe was doing something no human-made object had ever done before. It was diving into the sun, not orbiting from a safe distance, not peeking from afar. Actually inside the sun's outer atmosphere, flying through it at 430,000 miles per hour, with temperatures blazing at 2,500 degrees Fahrenheit on its outer shell, just 3.8 million miles from the solar surface. That is closer to the sun than Mercury, closer than anything humans have ever sent into space. And it survived. NASA's Parker Solar Probe had just written one of the greatest chapters in the history of exploration, not by going to another planet, not by landing on a distant moon, but by touching a star. Before we talk about the mission, we need to talk about the mystery. Because the Parker Solar Probe wasn't built just for thrills. It was built to answer one of the most frustrating unsolved puzzles in all of astrophysics, a puzzle that had been mocking scientists for over 6 decades. Why is the sun's atmosphere hotter than its surface? That sounds wrong, doesn't it? Think about it. If you walk away from a campfire, you get cooler. The further you go from the heat source, the colder it gets. That's just common sense. That's physics. That's how everything works. But the sun breaks this rule completely. The surface of the sun, the part we can actually see, called the photosphere, burns at around 10,000 degrees Fahrenheit. Hot, yes, but manageable in cosmic terms. But then something bizarre happens. The moment you move away from the surface into the sun's outer atmosphere called the corona, the temperature doesn't drop, it skyrockets. The corona reaches temperatures of 2 million to 3 million degrees Fahrenheit. That's not a typo. The sun's atmosphere is 300 times hotter than its surface. This mystery was so embarrassing to physics that some scientists quietly called it the coronal heating problem, one of those problems that makes textbooks awkward. The sun is our nearest star. It's been studied for centuries with the most powerful telescopes ever built. And yet, we couldn't explain why its own atmosphere behaved in defiance of basic thermodynamics. The answer was almost certainly somewhere in those inner layers of the solar atmosphere, in the region where the solar wind is born and launched into space. But getting there? That was the problem. Nobody had ever been able to reach that zone until Parker Solar Probe. You might think going to the sun would be easy. It's right there after all. Just aim at it and go. But going to the sun is actually one of the hardest things you can do in the solar system. Harder than going to Mars. Harder than reaching the outer planets. In fact, it takes roughly 55 times more energy to reach the sun than to reach Mars. But why? Because of a concept called orbital mechanics, and specifically something called Earth's sideways speed. When you launch a spacecraft from Earth, it doesn't just leave from a standing start. Earth itself is already hurtling through space at 67,000 miles per hour as it orbits the sun. Everything on Earth shares that speed. So the moment Parker Solar Probe left the launch pad, it was already moving sideways at 67,000 miles per hour. To fall toward the sun, you don't want to move sideways. You need to slow down. Lose that sideways velocity so gravity can pull you inward. But slowing down from 67,000 miles per hour in space, it requires an enormous amount of fuel, more than any rocket could practically carry. The engineers at Johns Hopkins Applied Physics Laboratory solved this problem with one of the most elegant maneuvers in spaceflight history. They used Venus as a brake. Here's where the mission gets genuinely clever. Instead of brute forcing its way toward the sun with rocket engines, Parker Solar Probe used Venus's gravity to gradually steal away its orbital speed. Over the course of 7 years, the spacecraft performed 7 Venus flybys, each time swinging past the planet at precisely calculated distances and angles. allowing Venus's gravity to tug on it just enough to reduce its speed relative to the Sun. Each flyby dropped Parker's closest point to the Sun a little further. When Parker's solar probe dove to its record closest approach, it was moving at 430,000 miles per hour. Let's sit with that number for a moment. At 430,000 miles per hour, you could travel from New York to Tokyo in under 1 minute. You'd cross the distance from Earth to the Moon in about 34 minutes. This is the fastest any human-made object has ever traveled, by a significant margin. And here's the fascinating physics behind why it goes so fast at that point. It's the same reason water in a river speeds up in narrow sections. As Parker falls deeper into the Sun's gravity well, gravitational potential energy converts to kinetic energy. The closer you get to such a massive object, the faster you fall. At 3.8 million miles from the surface, Parker was deep in one of the most powerful gravitational fields in our solar neighborhood, and the Sun was essentially flinging it around at record-breaking velocity. Now we arrive at the part that makes engineers either extremely proud or extremely nervous. At 3.8 million miles from the Sun, the temperature that Parker's solar probe's front face endures is nearly 2,500 degrees Fahrenheit. That's hotter than lava, hot enough to melt steel, hot enough to vaporize many metals entirely. And yet, just a few inches behind the shield, Parker's scientific instruments sit at a cool 85 degrees Fahrenheit, roughly room temperature. But how? The answer is one of the most ingenious pieces of engineering in NASA history. The thermal protection system, a heat shield that sounds almost laughably simple when you first hear about it, and yet performs a near miraculous function. The heat shield is 8 feet in diameter and just 4.5 inches thick. It's essentially a sandwich made of 3 layers. Layer 1, the front face, a sheet of carbon-carbon composite less than 1/10 of an inch thick. This material is essentially superheated graphite, similar in chemistry to the carbon fiber in high-end tennis rackets or golf clubs, but treated to withstand extreme temperatures. It faces the Sun directly and bears the brunt of the solar radiation. Layer 2, the middle part, about 4.5 inches of carbon foam. And here's the key. This foam is 97% air. It's essentially structured emptiness, a rigid lattice of carbon holding together mostly nothing. Carbon does conduct heat, but there's almost no carbon there to conduct through. The foam is so light that it was originally developed as a bone replacement material in medicine. Yes, the same technology used in human bodies is helping a spacecraft survive inside a star's atmosphere. Layer 3, the back face, another thin sheet of carbon-carbon composite completing the sandwich. The corrugated cardboard design, thin sheets plus foam core, gives the shield its structural rigidity while keeping the whole thing at just around 160 pounds. Light enough to launch, strong enough to survive. The white coat that reflects starfire. But carbon foam alone wasn't enough. Even with almost no material to conduct heat through, the shield still needed to reject as much solar energy as possible before it even entered the structure. So the engineers at Johns Hopkins developed a special white ceramic coating sprayed across the entire sun-facing surface. White reflects light. The coating was specifically formulated to bounce away as much solar radiation as possible, essentially giving the shield a mirror-like rejection of incoming energy before it can be absorbed. The result is dramatic. The front face of the shield reaches 2,500 degrees Fahrenheit, while the back face sits at a 600 degrees Fahrenheit. And behind that back face, separated by vacuum and the spacecraft's own structure, the instruments stay near room temperature. Here's another engineering challenge nobody thinks about. Parker's solar probe runs on solar power. It needs solar panels. But solar panels that are constantly exposed to the intense radiation this close to the sun would literally melt. So the solution? The solar panels are designed to fold inward as the spacecraft gets closer to the sun, reducing their exposure angle. The panels track the optimal position to generate power without overheating, and they have their own small cooling systems using pressurized water to carry heat away. Here's one more challenge. When Parker is at its closest approach, it's essentially unreachable. Communications with Earth face significant delays, and the intense radiation from the sun interferes with radio signals. The spacecraft cannot wait for instructions from ground control. So Parker's solar probe is designed to autonomously manage itself during the most critical phases. Onboard sensors monitor its orientation constantly. If the probe drifts even slightly, an edge of an instrument could peek out from the shadow of the heat shield and be destroyed in milliseconds. The spacecraft corrects itself automatically, keeping everything precisely aligned with the shield between it and the sun at all times. The navigation system tracks stars to orient itself. Even in the blinding proximity of the sun, it uses the positions of known stars to know exactly where it is pointing. All this engineering would mean nothing without extraordinary science, and Parker has delivered abundantly. Discovery number 1: switchbacks. One of the first big surprises Parker encountered was something nobody had fully anticipated. The solar wind near the sun is not a smooth, steady stream. It's crinkled with enormous S-shaped reversals in the sun's magnetic field, like a river that suddenly flows backward before resuming its forward course. Scientists named these structures switchbacks. Each switchback is a dramatic fold in the magnetic field lines streaming out from the sun, where the field momentarily reverses direction before snapping back. They appear everywhere in the young solar wind close to the sun, literally hundreds of them detected on early passes. Why do switchbacks matter? Because they carry enormous magnetic energy. As they travel through space and eventually straighten out, that energy has to go somewhere. And somewhere likely means into the plasma of the corona and solar wind, helping to heat it and accelerate it. They could be a key piece of the coronal heating puzzle. In 2024, scientists announced that the fast solar wind is in part powered by these switchbacks, solving a 50-year-old mystery about one of the two main types of solar wind. Parker helped pinpoint exactly where these switchbacks originate, at patches on the visible surface of the sun where magnetic funnels form. Discovery number 2: the corona's wrinkled boundary. When Parker first crossed into the solar corona in April 2021, making it the first spacecraft in history to enter the sun's atmosphere, it found something unexpected. The outer boundary of the corona, called the Alph-Venn critical surface, the point where the solar wind breaks free from the sun's magnetic control, is not a smooth sphere. Scientists had assumed the corona had a relatively clean, uniform outer edge. Instead, Parker found it was wrinkled with spikes and valleys, bumpy and irregular, like a lumpy cloudscape rather than a clean sphere. Some regions bulge further from the sun than others. Some dip inward. This completely changes models of how the solar wind forms and escapes the sun's gravitational and magnetic grip. Discovery number 3: 2 solar winds are different animals. The sun produces 2 main types of solar wind: a fast version, traveling around 440 miles per second, and a slow version, around 220 miles per second. Scientists had long wondered whether they came from the same places and processes, or were fundamentally different. Parker is revealing they are distinct phenomena with different origins. The fast solar wind is connected to those switchbacks, originating from open magnetic field regions near the poles. The slow solar wind, Parker's data increasingly suggests, comes from a completely different mechanism. Emerging from the equatorial regions where the sun's magnetic field is more complex and coronal material can leak out in a more gradual way. Understanding the slow solar wind is crucial because it's the type that most commonly sweeps past Earth, affecting our satellites, power grids, and communication systems. Discovery number 4. Seeing space weather being born. Perhaps the most practically important thing Parker has done is allow scientists to watch space weather events forming at their source. Space weather, solar flares, coronal mass ejections, geomagnetic storms can knock out satellites, disrupt GPS, overwhelm power grids, and endanger astronauts. Currently, our warning time for major events is limited because we can't see them developing until they're already well on their way. Parker is essentially a weather station inside the sun's atmosphere. The closest ever images captured in July 2025, taken during the December 2024 flyby, show the solar wind racing out from the corona in real-time detail never seen before. Scientists are now actively studying these images to understand the fine structure of the corona and how energetic events are seated in its depths. When Parker made its historic Christmas Eve close approach in 2024, there was a period of agonizing silence for the mission team at Johns Hopkins APL. During the closest part of the approach, the spacecraft was completely on its own. No communication, no real-time monitoring, no ability for ground controllers to intervene. The sun's radiation made contact effectively impossible. Parker was alone in the corona of a star, navigating by starlight, protecting itself by autonomous instinct. The team could only wait. The protocol was straightforward. If Parker survived, it would send a pre-programmed beacon tone, a simple radio signal essentially saying, "I'm alive." If the signal didn't come, it would mean the spacecraft had been destroyed somewhere in the solar atmosphere, becoming the most spectacular and expensive piece of interstellar ash in human history. On December 26th, 2 days after the close approach, the beacon arrived. The signal received at the Mission Operations Center at Johns Hopkins APL in Laurel, Maryland, confirmed Parker was healthy. All systems were operating normally, and it had survived its deepest dive into a star. The team who had spent years designing, building, and operating this spacecraft, who had poured their professional lives into this mission, received that signal and erupted in celebration. There is something profoundly moving about humans waiting in anxious silence for a tiny spacecraft millions of miles away to signal back, "I made it. I'm okay." So, has Parker actually solved the mystery that launched the mission? The short answer: we're getting tantalizingly close, but the full answer is still unfolding. There are currently 2 leading schools of thought. Theory 1, wave heating. Waves in the magnetic field, called Alf-Vän waves, propagate outward from the surface and deposit their energy in the corona, heating it as they dissipate. Switchbacks may be manifestations of these waves. Theory 2, nanoflare heating. The corona is constantly being heated by millions of tiny magnetic explosions as tangled magnetic field lines snap, reconnect, and release energy. Too small and too rapid for telescopes to see individually, but collectively pumping enormous amounts of heat into the coronal plasma. Parker's data supports both mechanisms operating to some degree, and the current thinking is that the answer may involve both, working in different regions and different conditions. The energy budget of how much each contributes and where is still being worked out with each new pass through the corona. This is a fair question. We are spending enormous resources, money, time, and human ingenuity, sending a spacecraft to do laps inside the sun's atmosphere. Why should anyone living on Earth care? The space weather connection is the biggest practical reason. Our modern civilization is astonishingly dependent on technology that is vulnerable to solar storms. GPS systems that guide everything from smartphone apps to airline navigation. Power grids that serve billions of people. Communication satellites, the International Space Station, and future astronauts on the Moon and Mars. Parker Solar Probe is our early warning system in development. By understanding how and where solar storms form, watching them at their birthplace in the corona, we can build better prediction models and give power grid operators, satellite controllers, and space agencies more time to prepare. Even an extra hour of warning could be the difference between controlled shutdown and catastrophic failure. And understanding our sun better helps us understand all stars. On August 12, 2018, a 91-year-old man sat at Kennedy Space Center and watched a Delta IV Heavy rocket, one of the most powerful rockets ever built, thunder off the launch pad in the pre-dawn darkness. Aboard, it was a spacecraft carrying his name, headed toward the star he had spent a lifetime studying. Eugene Parker had first predicted the solar wind in 1958. He had faced ridicule, dismissal, and the particular frustration of being right before the instruments existed to prove it. He had watched the slow accumulation of evidence over decades as mission after mission inched closer to confirming his theories and revealing the sun's deeper secrets, but never quite got close enough. So if you enjoyed this video, make sure to hit that like button, share it with your friends, and don't forget to subscribe for more amazing content.